Good afternoon. My name is Paula Itzel Sarco Ramos. I'm going to be presenting atomic and nuclear physics for my project for Physics 2. I decided to choose this topic because I'm pursuing a career in chemistry, and it is very related with chemistry topics that I already saw before in my classes. So I thought it would be interesting to look at the applications and investigate further about it. So I'm going to be presenting. The history of nuclear medicine has evolved over a century. This is because it is looking forward to enhancing diagnostics and treatments in healthcare or the medical field. So it all started in the 80s, 96 with the discovery of radioactivity. This was thanks to Henry Becquerel's discovery, and he started to investigate phosphorescence in uranium and unexpectedly found that these salts emit rays that can penetrate solids. So it's kind of like the discovery of X-rays, like the beginning. This wasn't really related directly with medicine, but it opened a path for the physics in medicine. Then we have in 1913 the first medical use of isotopes in plants. This was because of George of Hevesy. He was actually using this to investigate the absorption and translocation of lead in plant systems. So that's the second most important one. Then we have the cyclotrons. This is a device that was invented by the physicist Ernest O. Lawrence, and this device worked at accelerating the charged particles to high energies, enabling the bombardment of materials to produce artificial radionuclides. So research was often based only on radionuclides, which were really scarce and rare in that epoch. So this was very important. Then we have radio iodine in thyroid studies. This was thanks to Saul Hertz's research and all of his colleges in Massachusetts General Hospital. They started using radioactive iodine um, to use it in a therapeutic application for hyperthyroidism, and later it became important for the treatment of thyroid cancer. We continue with the first diagnosis scans. This happened in 1950s. This I put a picture here of the X-rays, MRA, MRI, and PET scans. Also, we have that these were like starting to emerge to develop brain and liver scans. So these scans provided unprecedented insights into the functioning of internal organs that we couldn't really see before, and it was pivotal moment in medical imaging. Then we have the PET and SPECT imaging in the 1970s and 1980s. These images, the positron emission tomography and the single photon emission computed tomography. They both offered it's just structural imaging, but they provided functional and metabolic information. They were effective in detecting metabolic activity in tissues, making them highly valuable in oncology, which is the treatment, the study of cancer, neurology too, and cardiology. Then we have the from the 1990s to the thousands, 2000s, and actuality right now, that the therapeutic advances. So for this, radioimmunotherapy is really frequent right now, and also targeted therapies. Right now, the medicine is evolving to be more personalized. So instead of being really general with people and how all the people work, they actually look into the person itself and it's also very common and popular with the improvement of cancer treatments. Um, about atomic and nuclear physics, while both branches comprehend the atom and its components. Atomic physics is more focused in the study of atoms as an isolated system of electrons and an atomic nucleus. So it mostly comprehends the electrons in the atom, while nuclear chemistry focuses more in the atomic nuclei and all of its interactions, how it behaves and how it affects other systems, and it also investigates protons. So that's the main difference between atomic and nuclear physics. But they both have these nuclear interactions, including radioactive decay. It also has this beta and alpha decay, and capture reactions. That this is when a system is bombarding electrons and some of them are captured. Nuclear fusion and fission, and also explosion reactions. For medical applications, one of the most important uses of nuclear radiation is the location and the study of diseased tissues. This application requires a special drug that is called radiopharmaceutical, and this radiopharmaceutical contains an unstable radioactive isotope. So when this drug enters the body, whether it is via bloodstream or ingested, it tends to concentrate in inflamed regions of the body. It's also known that cancer cells, they absorb more of this isotope of this substance, and these radiopharmaceuticals also call it radioactive tags because they allow doctors to track the movement of drugs in the body. In this case, the one that they specifically use, these are used to monitor the function of body organs, such as blood flow, heart muscle activity, and iodine uptake in the thyroid gland. So here I put an image of the brains that use the radiopharmaceutical drug. These colors indicate the relative metabolic or biochemical activity. Red indicates high activity, and blue the low activity. So this one shows a picture of bipolar brain PET scans. The first one is the preset. It has a lot of low activity. Then we have the normal, and then we have another one. So it is very useful for not also for health diseases, but also for abuse of substance. It really is referring the picture of a normal brain. We compare it with an alcoholic or a drug addict, and with people who are mental ill. I decided to show the relation of nuclear and atomic physics with the medical field, using as an example the positron emission tomography, or PET, and how it works. This scan, it really utilizes the principles of nuclear physics, specifically the radioactive decay and particle interactions. So when this whole process starts, we begin with the pharmaceutical drug that I talked about, or the tag that is used. It is consumed or injected in the bloodstream, and then it gets absorbed mostly by the most inflamed regions of the body, or cancer cells, and then this when the tracer uptake is done, they tell you to wait, and it's done. Then it's when the radioactive decay and positron emissions are more unstable. So these scans use the radioactive isotopes and its instability. These isotopes emit positrons, which are positively charged electrons. Positrons are not found in the human body, and they are produced artificially for use in the PET scans. Then we have annihilation, when a positron encounters an electron and they annihilate together. So produces an high energy photons or gamma rays, and they travel in opposite directions, which are like detected for the scans. But the PET scanner has a ring detector around the patient. I put a picture there where the ring is, it has the patient in the middle, and these detectors detect the two photons simultaneously, which allows the scanner to pinpoint the location of the annihilation event. The detectors convert these gamma rays into visible light photons and then into electrical signals, which then are processed by the scan, and then the image is formed. The scanner measures the time it takes for the photons to reach the detectors, and then we get the pictures that I showed before.